chat thing on
Yeah.
YouTube?
I have only OBS open. Let me see if I can go live here. Okay,
Okay.
I'm going live. Oh, I need to record.
All right.
1 second. Um, okay.
All right. All right. We're live.
All right. Can you do a quick sound check because there's a system change? No echo.
I think it should be fine.
Okay. Let's get started.
Audience, let us know if there's any echo.
All right. All right. Hello, everyone. Welcome to today's brand new episode of Corecast. I am your host, Tim.
And I'm Mikey.
And I'm Sile. Welcome, everybody, to a brand new exciting episode of Corecast. If you haven't already, do join our Discord channel. And if you're watching on YouTube, where we do this every Tuesday, 5 p.m. Pacific, 8 p.m. Eastern, do ask us questions during the episode, and we'll get to them. So let's get to it. Um, so I guess Tim and Mikey, I remember from when learning high school physics, there was no concept of like a cosmic speed limit, and I could imagine like, oh, you can travel infinitely fast. But then when I learned relativity, that's definitely not the case. There is a upper bound which happens to coincide with the speed of light, as we've talked about in our many, past episodes. And in particular, I wanted to explore with today's episode and like what would it be like to approach that speed of light? I don't think that's talked about as much. It's just talked about you can't go faster than light, but like as a being that has mass and obviously moves slower than the speed of light on my day-to-day basis, I just want to go into what that would look like. And so I guess Tim, can you essentially like give a kind of I guess like description of what that would be like, and then we can kind of work our way up to that.
Mm. Yeah. So the interesting thing about these sort of scenario is that the mathematics of the physics it turns out that it looks surprisingly like falling into a black hole, and we'll explain why. And this means that literally, if you try to, if you get on a spaceship and try to approach the speed of light, in the real sense, it's kind of like going through a portal. So the sci-fi conception of warp drive actually, it's kind of not that bad of an analogy, but we're gonna unpack all that sophistication. So
So, so are you saying that the analogy, like, I mean, back when I was a kid and there was Star Wars, I would imagine like, they talk about, oh, like going at the speed of light from one end of the universe or one of the galaxy to another galaxy. And it's basically like a Millennium Falcon going like through a portal that's all like blue and you just fall through. Is that like as far-fetched?
I mean, there's some like artistic choices in rendering those images. It's probably not exactly like that, but I would say, I don't know if Mikey, you would agree. There's going to be some kind of warping, I think.
Oh yeah, in terms of the visual effect, yeah, I would say uh, the bigger effect would be that if they actually did get close to the speed of light, um, when they got from one place to another, they would find that everyone they know has died of old age, and that thousands of years would have passed in the outside world.
Quite a downer there, Mikey. Just started the episode. Already
Yeah.
already very much on a more morbid note.
Oh, I'm just saying
Um,
it would be really
mhm,
hard to orchestrate an intergalactic war if everybody's
mhm.
clocks are moving at different speeds.
Yeah, actually, you bring up a really good point. So in relativity, we know that people's clocks go differently depending on how you're moving relative to somebody's other reference frame. So I guess I wanted to pose the question, is moving at the speed of light, is that a well-defined question in terms of how we've asked it? Tim, I'm going to point this to you.
Yeah, I think at face value, it's not really well defined because, like Einstein says, the velocity or speed is always relative. You can't just say I'm moving at the speed of light. Like it doesn't make any sense. You're only moving at a particular speed relative to something else. And well, I guess exactly at the speed of light, there's kind of an exception to that.
Mhm.
So if I say I'm moving really fast, a lot of times it's implicit in that statement that we're moving really fast relative to something, and usually that's Earth, right? So and I guess in the universe it's a little more vague, like moving fast with respect to what, right? But some of the galaxies could be moving pretty fast. So in any case, when we say moving fast, close to the speed of light, um, we need to think about with respect to something. Like we need to think of references and whatnot.
Mhm.
Light travels at the speed of light relative to everything. Explain
Right.
that.
Yeah. I would say that is the exception. So speed of light is unique in that it doesn't matter what your reference frame is. If you move at the speed of light, everything else move. Everyone would agree that you move at the speed of light. Although the light itself will shift and change, but that is one exception. Anything below the speed of light is subjective in some ways.
Yeah, fair point. Okay, so when you talk about moving at the speed of light, we're talking about relative to some other object. Just it's not an absolute sense. I mean, rather, sorry, approaching the speed of light, not moving at, but approaching the speed of light, relative to some other body, for instance. So one question I have to ask is like, in relativity, if I'm moving at a certain speed. I could view it as like, oh, I'm moving through space at a certain speed, or oh, like I'm stationary and the rest of the universe is passing by me at the opposite velocity, for lack of better words. So I guess like how do you think about that, Tim?
I mean, technically, that is a valid perspective, right? I mean, that is
Yeah, what
valid.
you said is correct. What's there to argue?
Yeah. I mean, although I would argue, I guess one could the argument that there is a rough, approximately universally agreed upon reference, kind of like on Earth, right? Like everyone on Earth, when you say you're moving fast, it's not that ambiguous because like even if I say, oh, a plane is moving, I don't know, 600 miles per hour, I don't have to say, well, with respect to what, because people all agree that it's with respect to the Earth. And like someone on the South Pole versus North Pole versus in America, this notion that a plane is moving fast is unambiguous. I mean, in the universe, not everyone, I guess aliens or other species outside of humans, not everyone agrees on the Earth's definition of stationary. But there is something called, I guess, the cosmic microwave background. There's this afterglow of the Big Bang that kind of approximately set a stage for the average kind of stationary reference in the universe. I think that's
Mhm.
fair. Would you say so, Mikey?
Yeah, yeah.
Can we take like 2 seconds to describe what this microwave background is?
Oh, damn it.
All right, Mikey, I'm going to point this to you since
Wait,
you seem
damn it.
most enthusiastic.
I guess the only reason this is an issue is because a lot of people uh, fall into this the misconception that the universe has no reference frame. Everything is just moving, and that there's no one true um, it's just empty space. But as Tim mentioned, there's like a bunch of stuff left over from the Big Bang, and when you look at all that stuff from the Big Bang, there actually is kind of a universal stationary point of the universe. And so you could, if you wanted to, define some kind of universal speed where similar to the how you say I'm going 60 miles an hour in my car, relative to the ground. You can kind of say something similar to that with the universe, but yeah, that's it.
Okay. All right
Hmm.
then. We'll just leave it at that unless anyone asks questions about that. So one thing I want to touch upon is like right now we've talked about like moving at a certain speed, but to get to that speed we need to accelerate. So I guess Tim, can you describe like how acceleration plays a role in this? Like as I accelerate from like let's say from stationary relative to Earth. and just go on a rocket ship, and I'm just like, I don't know, it was my best rocket ship impression, but going at like
Oh,
just hitting
right.
the gas and just going, what happens?
Yeah, I would say that one thing to keep in mind is that there's a general concept of time dilation and length contraction. So
Hmm.
as you move, things that depending on how fast you're moving relative to the let's say the stationary background of the universe, the cosmic wave background. Depending on how fast you're moving, the farther you are, the more you see the universe kind of get squashed in that particular direction, right?
Hmm.
So as you accelerate, that squashing effect is gonna like get more and more pronounced, right? And
Hmm.
also you see time around you, like outside of you, getting slowed down, right? And also
Hmm.
in the same way, people from the outside looking at you and the spaceship, they will also see that hey, the time relative to them is slowed down. So in a very real sense, as you approach that speed of light, what you see
Hmm.
of the universe will kind of change in a really weird way. Like it's probably not very intuitive. Like the concept of space will shrink and time will get dilated
Hmm.
depending on if you're looking ahead or behind. And in kind of like a weird way, I would imagine perceptually the it will look very different. The universe. It will look very weird.
Hmm.
Well, it look like a pancake.
Does doesn't that mean like you'll be at this like imagine you're moving very close to the speed of light? I assume then by length contraction, the universe will effectively like in the direction you're moving be squashed almost like a plane, like a flat 2D sheet, but the very tiny thickness. Like wouldn't you just like be able to reach anything? Like 'cause you'll be at the same kind of like level. Let's
Yeah,
say I like
exactly. From
was
your perspective, it would take zero time to reach anything because
Right.
everything would be
oh.
so close. But from the outside, it looks like you're frozen, and that's why you think it takes zero
Mhm.
time to reach anywhere.
I guess can we unpack that a bit more, Mikey? That's really interesting.
Yeah, right. So the as we mentioned, the faster you go, the more the universe is what's the word? What do you do to a
Compact,
pancake?
like shrunk in that direction, like
Yeah,
that
it's shrunk in that
dimension.
direction. So the universe, imagine the
Mm,
universe is a sphere. You start traveling closer to the speed of light, um, that sphere starts shrinking in size, right? So if you
mm,
actually, let's say, got to somehow were able to like break relativity and achieve the speed of light, then the universe
mm,
would be two dimensional. It would be a two-dimensional
mm,
disk. From your perspective, it would take zero amount of time on your watch. The second hand wouldn't even pass on your watch as you got from one end to the other because it's so close to you now. And
mm,
this kind of aligns with what an outsider would see if they were watching you zoom by. They would also see the clock on your watch not moving at all. They would see you
mm.
frozen in time. Um, so from your perspective, you got to the end of the universe instantly because the universe was so small. From the outside perspective, you got to the end of the universe so quickly because you were frozen.
But hold on a sec. Okay, if I'm in the spaceship moving and I see like the universe compact, I can understand the zero time, like because I'll be effectively touching both ends of the universe like at the same time. So I mean, yeah, there'll be zero time. But if I'm from looking from the outside, the universe is not shrunk, or like the
Yeah,
universe is still like it's spherical shape.
yeah.
So what gives? Am I like am I stretched out? So I'm at like all places at once, or like what does that mean?
No, you're not stretched out. It's just like I guess the way I would think about it is like I could if I was going at the speed of light, I could get from one end to the universe without aging, without even aging a little bit.
Mm,
For me, that's because it's so close. From the outside, the explanation for why I'm not aging is
mm.
because I'm frozen.
I see, I see. So that means that like you could say photons don't age.
Yeah,
Yeah.
photons do not
Okay.
age.
Although I would like to add one thing. This is the classic twin paradox, right? So from the space. So from people outside looking at the spaceship, people inside the spaceship seems like they're frozen in time. But from the spaceship's perspective, people outside are also frozen in time. So it seems like, who is aging more? There's a discrepancy.
Mhm. I see. So is there anything which talks about this, Tim? Like how do we kind of like resolve this or how yeah, I guess is there a resolution to this or it sounds like, from my perspective, one thing's happening, from your perspective, a different thing is happening.
Yeah, the
When you
resolution.
you will agree.
Sorry.
Oh, I was gonna say when you meet up, you will agree.
Yeah. So that's what's interesting about acceleration, right? Because when you're moving really fast, you can have two very different perspectives. Because if I'm in a spaceship, I'll never really talk to the people on the ground. In order to talk, I have to slow down and just kind of imagine I'm speeding up. This length contraction thing will slowly increase actually. So the way I see the universe is that it's going to shrink, 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 shrink. And as I
Hmm.
slow down, let's say, to catch up with somebody else, or let's say I take a round trip back, right? Then,
Hmm.
then, then, in a very real way, the universe outside, the way I see it, is going to like expand, 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 and then contract, 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 contract again. And then all that time, um, and eventually, during this acceleration, when I go from one way to another, you will see the time pass by finally, right? And then
Hmm.
even for the people in the spaceship, as you go through this acceleration of turning around, you will see all those years of universe progressing, wars, intergalactic wars, whatever, happen. And then as you come back, you will finally also agree with let's say people on Earth, but hey, guess what? I haven't aged a single bit, but whatever's happening on Earth is all different now.
Hmm. Hmm. Okay, so the main crux of it is like in order for you to meet one party, I'm gonna use a party for lack of better words, has to like turn around. In order to turn
Yeah.
around, you have to accelerate, essentially.
Yeah, yeah, and acceleration is key here. I mean, I think in a lot of
Mm-hmm.
high school physics, people only talk about speed,
Mm-hmm.
but the acceleration is key. And one of the key point, and why is this such a big deal? One of the big deal is Einstein's equivalence principle. Acceleration is actually equivalent to gravity, and that's what makes it important.
Mm. Can you or Mikey explain what the equivalence principle is before we move forward?
Yeah, sure. I guess just said simply, the equivalence principle is something that Einstein noticed allegedly during a thought experiment, where if you've ever been on a roller coaster ride or been in a car that's accelerated really fast, you feel some force pushing you back, and
Hmm.
that force is due to the your inertia, your tendency to not want to accelerate, to not want to change your
Hmm.
velocity. Um, and Einstein's thought experiment was to try to determine if there's any way to distinguish this force you feel from acceleration with the force of gravity, um,
Hmm.
because they're similar in a lot of ways. We mentioned before about how gravity is kind of different from the other forces because everything feels it. There's no such thing as gravitationally neutral. Like with electric charges, they can attract or repel, attract or repel, but only if they
Hmm.
have some charge. If they're neutral, they don't feel any force. But there's no such thing as gravitationally neutral. Everything feels the force of gravity. Similarly, everything feels a force when under acceleration. And so Einstein kind of looked at these two things and were like, is there any way to distinguish them?
Hmm.
And the conclusion he came up with is no, that the force of gravity is completely equivalent to the force you feel when you're accelerating. And well, that was kind of it's historically famous because that was sort of his guiding principle when developing the theory of relativity.
Hmm. Well, one question I have about that. So you brought up an interesting point that like everything feels gravity, but but not everything feels like the force of electromagnetism, especially neutrally charged particles. And so my question is, if you have, let's say, you're like a proton and you meet another proton and you get like pushed away and you feel this like I'm feeling quotes this like force pushing you away. Is that the same as gravity even? Like any force? Like because most of the forces that we experience as humans is like electromagnetic repulsion. So I'm
Yeah.
wondering in that case, like how do you think about that?
Wait, sorry. What's the question? Is you're asking if the
So
force?
the Yeah, so my question is if you have a force that's causing an acceleration that's due to an electromagnetic force, and you're talking about this equivalence principle that you can't distinguish between acceleration and the force of gravity, but you know that the force is coming from electric charge, like the two charges, like charges repelling each other. Can you still say that that is indistinguishable from gravity, or like what are your, yeah, I just want to better understand that.
Um.
Well,
Uh,
I mean, the
yeah.
equivalence breaks,
If
right?
we were if every single human being had a charge of plus 200, and we were sitting
Hmm.
on an Earth that had a charge of minus 200, it might
Hmm.
be difficult to distinguish that from gravity.
No,
It might be hard to distinguish from gravity.
Sorry.
Oh no, go ahead, Tim.
no, but I think that there's going to be self-repulsion, right? Like some aspects of it will be similar, but you can run an experiment to distinguish it, right? Like, if we
Hmm.
all have plus 200 charges, we will repel each other. So it
Hmm.
wouldn't be exactly the same. So I think this universal behavior is um, will be broken.
Hmm. Okay. Okay. So what you're saying is if actually that brings me to my next question. If and I just want to spend a little bit of time and then we'll move on to a different the next part. Um if the universe had no neutral charges, everything was charged, would the equivalence principle like be able to hold? Or is that like, yeah, I'm just wondering, like, it seems like the limitation for
Hmm.
not applying to electromagnetism is that everything doesn't feel electromagnetism. But if everything did feel electromagnetism,
Yeah,
then like,
there's a little more to it, right? Because gravity is
mm,
universally attractive, and that's a unique
mm,
characteristic that does not apply to any other forces. Like in
mm,
electromagnetism, there's repulsion. In the strong
mm,
force, there's also repulsion, and in the weak force, there's also repulsion. In most of
mm,
the forces that we know, there is attraction and repulsion. Of course, in
mm,
physics, we do have theories of how to derive gravity-like equivalence to forces,
mm,
but those are generally much more complicated, right? Um,
mm.
so this basic equivalence principle, I think, really only holds for just gravity and just generic acceleration.
Okay, that makes sense. All right, uh I think that that answers my question regarding equivalence principle and other things. So now I guess like Tim, why did we mention the equivalence principle? Like, why is this important in the context of this discussion?
Yeah, the reason is because when you undergo like imagine you're in a spaceship, you're constantly undergoing acceleration, and if you don't have any other information, you wouldn't be able to tell if that acceleration is because someone, I don't know, pressed a button on that spaceship. Let's say you didn't know there's an engine versus
Hmm.
um versus there's gravity involved. And as a
Hmm.
result, if you look at mathematics, what that person experienced in the spaceship, it turns out to be very similar to, let's say, let's say someone near the surface of a very close to the surface of a black hole. And the
Hmm.
reason is because when black holes are sucking things in, there's a constant gravity that is inevitable. It forces you to feel it, and that's similar to if you buy the equivalence principle, that's very similar to a constant acceleration.
Hmm. Gotcha, gotcha. That makes sense. So what you're saying is like if I'm in a spaceship and I'm moving really like I'm accelerating a lot, that can be, and I wasn't able to see the outside and I was in the spaceship by itself. it could almost be as if like I was, standing on something that's maybe like orbiting a black hole without falling in, or some have like highly massive object.
Yeah, yeah. I mean, that's roughly the point. And it turns out if you look into the math, many of the and if you buy this equivalence principle, many of the attributes about black holes actually translate to things you see when you're accelerating, when you are trying to approach the speed of light. And the equivalents are pretty striking.
Wow, I mean, so now we've come to the crux of this episode. So I follow you so far in terms of if you're accelerating. Actually, quick question about accelerating, like uh, you know, am I constantly accelerating or like what is the process like? Like just kind of walk me through the more pragmatics of it. Like say I strap this like super really huge like amount of fuel to a rocket and I'm just like I'm just gonna go. I don't care. I'm just like do or die. Like I'm just gonna go for it. Um what are the barriers to like stop me from like reaching the speed of light? Like because if I look at it classically, I just need to keep accelerating and eventually I'll hit it in some like finite amount of time. But in relativity, that might be different. So can you describe to me what is the difference here?
Yeah, yeah. I mean, in relativity, you never quite reach it. You asymptote to getting close to the speed of light, and in that process, you
Mhm,
see kind of the universe. Something about the universe will kind of change in a way.
mhm,
Because of length contraction and time dilation and whatnot. And also, there's
mhm,
going to be effects of blue shift and red shift, right? So
mhm,
things that are trying to catch up to you, they will never be able to catch up. And you can go to the math. If you're constantly accelerating, even light, it turns out, will not be able to catch up to you. And also, um, and also, I believe there's a limits on the type of signal that you send. But so in any case, yeah. As you accelerate, you're gonna undergo this process, and it kind of looks like a Portal esque description, basically.
mhm, mhm. I also remember you mentioning that like as you accelerate, you'll reach closer and closer to the speed of light. You'll see particles and antiparticles appear. This was like in a previous episode some amount of time back. Could you
Yeah,
also describe that as well?
yeah. This is basically an independent calculation that people did. It turns out that if you're constantly accelerating, and then the space time is kind of changing in front of you, because remember, like the universe is becoming more and more like a pancake. This kind of disturbance in the space time in front of you will appear. It will appear like there are particles charging right at you. And so, in fact, you might actually just die from if you're in a spaceship from the radiation. But let's say you survive that. And it turns out that this calculation is very similar to the Hawking radiation, right? So you can argue that the when you're accelerating, you see particles
Mhm,
getting shower onto you, versus if you're near the horizon of a black hole, particles
mhm.
are hitting you because of Hawking radiation. Those are similar.
Gotcha. Mikey, question for you.
What's that?
What is Hawking radiation?
Um, uh, oh, in this context?
Yeah, like I mean, just to mention Hawking radiation. I just want to make sure we're like the audience is clear, like what that is.
Yeah, I don't know. Well, there's so many different ways to think about it. I think this is actually better for Tim to answer because he was talking about a specific aspect of Hawking radiation. I could describe what it is, but I don't think that would be as useful for this conversation.
I
All right, Tim, go for it.
I think the same description will apply, right? Because Hawking radiation can be viewed as particle antiparticle production, and then one of them escaping into the black hole. I think here you may be able to describe it as particle antiparticle production, but also because of the fact that you're accelerating, some of the particle will never catch up to you and just disappear. So to you, you only see some of the they don't in your point of view, they don't have time to annihilate again. So to you,
Yeah.
you will also see this Hawking radiation. So it's like imagine you're trying to get close to the speed of light, and then you're just pressing the button, just charging for it. You're like, well, I'm going for it, right? And all of a sudden, you see like Hawking radiation. You see things behind you falling into kind of like a horizon, never able to catch up with you. For a second, you might just panic. You'd be like, hey, dude, like, what have I done? Have I created like a black hole? Am I trying to escape from a black hole or something?
Hmm. So, okay, so when you say create a horizon, what does that actually even mean? I guess we've been, using the term horizon with black holes as the meaning probably the event horizon. And then you're talking about this horizon when you're clearly not in a black hole, you're just moving through the universe,
Yeah.
at a very, at high, yeah, at high speed.
Yeah, it's simply the fact that because you're accelerating so hard, you're trying to asymptote the speed of light. Not even light can catch up to you. I mean, that fact is not obvious, maybe to some of the viewer. But if you go to the math, like even as you asymptotic to this, if you keep accelerating, you're trying to get close to the speed of light. It turns out that not even light will get to you. It's only asymptotically they can get to you, but never. Like it'll take
Hmm.
infinite time. So, and this is kind of like black hole, right? Like if you fall into the event horizon of a black hole, well, you shine a beam of light, that light is not gonna get to me. So it's kind of like blasting in a spaceship, and I don't know, you left something behind, and it just no matter how hard that thing tried, it won't be able to catch up. But of course,
Mm.
in this
Mm.
case, you can change your mind and be like, hey, look, guess what? Let me just turn off the throttle and and pick up Sahil or whatever I left it behind.
Yep.
So that's the difference. But black holes is inevitable, and you can't do that.
Mm.
Mm.
So you're saying like me falling into a black hole, and then if I try sending signals to you once I don't know, not once you've fallen into a black hole, because it's hard to know when you actually have fallen in. I'll just see you go at the event horizon and slowly approach it. So similarly, like if I try sending you signals, so let's actually, this comes to my other question. Let's talk about the perspective from the observer who's like quote unquote seeing this, for lack of better words. Let's say you rocket ship and you go really, ways away, and I say,
Yeah.
okay, like Tim obviously is not reaching the speed of light. He'll approach it, but he won't quite reach it. So let me send him this light signal saying like some sort of message to you. So I send you a light signal. What do I see as an observer from the outside of you like going really, as you're going further away?
You mean in the acceleration scenario?
Yeah, yeah. Like say I'm on Earth and you're in a rocket ship that like can basically, futuristic, can approach the speed of light, with, relative more ease than the technology we have today. Um, And so you're going and I like say, hey Tim, you forgot your toothbrush. And I want to send you that signal. So, how does it? What do I see in terms of you going far away? Assuming I could like, see that far out.
I mean, if you press the throttle, well, either that signal might just miss me, but if I press that
Mhm.
throttle and just keep accelerating, assuming I don't release it, like max it out at a constant quote unquote acceleration, that light signal actually will never be able to reach me, basically.
I I got that. So I'm trying to understand like from the concept, like because we're trying to relate the analogy to black holes
Yes.
because you mentioned that like this is very similar to falling into a black hole. So from the perspective of a black hole, I can like understand like you're sort of red shifted and you become redder and fainter, and then eventually you kind of get plastered on like the surface of like the black hole or this event horizon of the black hole, for lack of better words. And and the light signal will take an infinite amount of time. But here, like as you're going far away, there is no black hole, and so I don't see you get plastered. Does you get plastered on anything? Like, is there any kind of effect like that?
I guess that's a good question. I think the analogy is not perfect. It's only locally
Okay.
valid. So if you take like a small
Hmm.
patch of the black hole and look at the physics there, it's similar, but it doesn't cover the
Hmm.
entire black hole. Um, I have seen some calculation on because this has to do with like the area of the black hole. All the information is on the area of the black hole. There have been some calculation to calculate also the area associated with this accelerating phenomena. But the analogy there is not perfect anymore because, like for stuff to get passed on it, I guess you need a little bit of extended volume. Um, but I think I don't exactly know the answer there. It's a little more
Mhm.
complicated. So I
Mhm.
can't give you a good answer right now.
Okay. That's fair. So I want to move to our next related conversation, which is the whole thing about if I'm gonna hopefully I don't mess up the acronym, ER equals EPR. And maybe the full acronym is not as important to know what it is, but this is more speculative territory, how like moving close to the speed of light could be viewed, and I use could in quotes, as a form of quantum teleportation. Now, Tim, can you comment to that and sort of set the stage for that?
I so I think in this episode we talk about these bridges in physics, right?
Hmm.
In physics, there are these analogies, and it goes a little further than that. It's more like mathematical equivalence. So there are like multiple ways to describe um, scenarios, right? So we talk about how acceleration can be similar to gravity, and in previous episode we also talk about how gravity can be viewed as entanglement. And if you follow this ER versus EPR paradigm, and this gets spelled out even more explicitly, it says that um, you know going traversing through a wormhole is similar to quantum teleportation. And in fact, like Google, the Google quantum computing lab has sort of demonstrated this loosely in a quantum simulation. Now, I think this is speculative. So if you view as if you view going to the speed of light, getting close to the speed of light, and then landing somewhere, from your
Hmm.
perspective, it's kind of like warping a little bit because the space time around you has changed. There's a horizon you created. It's almost kind of like you're escaping a black hole, and from your perspective, and landing somewhere else. It's kind of like going through a portal. And if you think of that as this wormhole and analog, I mean, it's not a wormhole. You're just literally speeding up and slowing down. I mean, there could be a quantum mechanical picture where you're kind of like teleporting from one place to another. I mean, the end result is the same. I mean, you can view it differently. And I think in my mind, it's a matter of perspective, right? There are different ways to view the same system and arrive at the same conclusion. And so it's interesting that, hey, maybe you can even think about this quantum mechanically.
Yeah, that makes sense. I guess, Mikey, do you have anything to add to that, or anything you would like to? Yeah,
No, my view, I guess I have a kind of a different, like, when it comes to ER equals EPR, everyone has a very different way of thinking about it. And this is pretty new to me, so I don't have anything to add to that.
fair enough. Fair enough. So in the remaining time that we have, I guess like I want to come, mention that that we've talked about that these aren't like pie in the sky ideas, but there are objects that are doing this in terms of like approaching close speed of light. Wasn't that what you had mentioned, Tim?
Oh, like neutrinos?
Oh, you mean like, yeah,
Yeah,
particles?
yeah. Or like just like what kind of, I guess, like what are the applications of like looking at things that move close to the speed of light, but not exactly at the speed of light?
Well, I mean, the universe, according to these particles, are very different. Like if you take their perspective, and 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 things like time dilation, length contraction, definitely have been observed. Like for example, cosmic muons come from the sun. They go to the Earth, and they normally they would have decayed long ago before reaching Earth. But because of this warping effect, in a sense, they're kind of able to, I don't know, be transported onto Earth safely. It's kind of like a type of, if you like to use the word teleportation, I guess you could. You can kind of think of it as like, hey, it got teleported, or it just moved from the sun to the Earth. So that perspective is definitely helpful. Although like these particles don't really have agency, right? I don't know. it's not like they're accelerating and then decelerating. They're just streaming out from the sun and then just hitting some material and self-destroying. Um, so I don't know. I don't know. I don't know if our discussion would hold to that much.
So, Mike, you had mentioned neutrinos, and I mean, these are particles we've talked about, and I mean, for the purposes of this discussion, they have a relatively like very, very light mass
Yeah.
and move close to the speed of light. So I'm wondering, I guess, Tim or Mikey, in the context of this discussion, do you think from like a neutrino's perspective, they like, see, I guess like all the effects that you've talked about, or like I'm just curious.
Oh yeah, definitely. Yeah. Neutrinos are almost frozen in time. Not that neutrinos have any like, it's not like they have things to do, or it's not like they were watches. It doesn't really matter for them. But and it's not like they evolve with time, or so it doesn't really matter to a neutrino. Neutrinos don't care.
Mhm. Yeah. Well, so we're basically almost at time. So I wanted to give you guys a chance in our tradition to leave the audience with any words of wisdom that you've learned from approaching the speed of light, if you've ever tried that. Go first, Mikey. You seem
No,
most eager.
Tim, you go first.
well, well, I would say that like like before Einstein's time, like people have never thought much of this phenomenon, right? They're like, oh, you can move at any speed, but it's kind of remarkable that um, as we approach this cosmic limit, with at least respect to the average universe frame of reference, the universe looks so different. And then as we accelerate to get to that speed, and it seems like it's such a simple thing, right? Literally, it's imagine aliens have this technology. I don't know if they do, and they're able to just like, hey, let's go visit some galaxy or whatever, accelerate, woo, and then like decelerate, and immediately they're faced with these very sophisticated physics phenomena, things like horizons, things like unraw radiation um, from quantum physics, and just from like I don't know driving their little spaceships, right? Um, and it just tells us that gravity has a lot of interesting bits, and probably quantum physics will come into it, um, and somehow you know, and then somehow things like black holes or the expanding universe and all these horizon issues, information, like they aren't just like some weird theoretical physics quirks that nobody should care about, right? Like these are real phenomenon. Like even just operating a spaceship, accelerating close to the speed of light, you are gonna face with some of these issues. So I think this just highlights, like maybe in many thousand years when we actually start to develop these technology, if we ever do, we better have a damn good understanding of these quantum gravity-esque phenomenon. So
Yeah. I guess just piggybacking off that, I would just conclude by saying that, like, I don't know, in all my years of studying physics, there's a couple things that physicists fixate on, and two of those things are the speed of light and black holes, because those are the two places that God never intended humans to go to. Um, and that's where all the mystery lies. Like funny things happen there in those two places. And yeah, we keep trying.
That's interesting perspectives from you both. Especially that's interesting to put it, Mikey. Uh, Bringing a more uh, bringing the notion of God.
Well, I just thought I was
uh,
Interstellar again, so it's you know.
yeah. So on that note, I want to thank everybody for joining us, and we'll see you all next week.
Bye
Yeah,
bye.
see you all next week. Bye.
Yep.